So today we're going to look at maxima and minima problems. Really, this is making use, this is applying differentiation that you've come across in pure maths into our functions of time. We can differentiate not only to go from one variable to the next, but to find the maximum value of any particular variable. If we want to find the maximum displacement, we'll have to calculate ds dt and set it equal to 0. If we want to calculate the maximum velocity, we'll calculate dv dt and put it equal to 0. And the maximum acceleration, we'll get that at dA dt equals 0. In this example, we've been told that a child is playing with a yo-yo, and the yo-yo leaves the child's hand at time t equals 0, so that's at the beginning of our observations, and travels vertically in a straight line before returning to the child's hand. So, you know how yo-yo works, up and down and up. The distance of the yo-yo from the child's hand is given with this function here. So s equals 0.6t plus 0.4t squared minus 0.2t cubed. We've been given a restriction. T is in between 0 and 3. So this model, this function is only valid when t is in between 0 and 3. And first we've been asked to actually justify that restriction. As we've seen up to now, it's really useful to get a diagram to be able to see what's going on and to be able to, in this case, justify the restriction that's been given. So, just going to start by simplifying or factorizing the expression we have here. I'm taking out 0.2t. That leaves me with 3 plus 2t minus t squared in the bracket. Something I can factorize in my head. We get 3 minus t and 1 plus t as factors. And that leads to some roots. The roots here are t equals 0, t equals 3, t equals negative 1. Okay, so what does this look like on a diagram? Just going to mark off the x-intercepts of these roots, and there's the sketch that I have of this function. Looking at this, we want to make sure we can make good sense of it. On the horizontal axis, we have time, and on the vertical axis, we have displacement. So the yo-yo leaves this child's hand when t equals 0. Okay, so let's just track what's happening on the diagram. So, the yo-yo is released from the student's hand when time equals 0. So we have that at the origin. And as it's going away from their hand, so as it's going down towards the ground, we can see the displacement is increasing. So that lets me know that down is the positive direction. So any positive values are telling us how far down and away from the student's hand the yo-yo has gone. So just looking through, it goes away from the student's hand, and then it starts to return to the student's hand, and it returns at 3 seconds. After 3 seconds, we seem to have negative displacement. This would mean that the yo-yo has gone through the student's hand and is now above their hand and continues to get further and further away above the hand. This wouldn't make sense. Equally, some of this function exists before 0. So this would be motion of the yo-yo before the student has actually thrown it. This doesn't make sense either. The reason for the restriction is the only part of this function that actually models the yo-yo leaving and returning to the student's hand is the part in between t equals 0 and t equals 3. So, to summarize that succinctly, I'm saying that when t is greater than or equal to 0, so when t is positive, so after the yo-yo has left the student's hand, the displacement is positive only in between t equals 0 and t equals 3. So, I set two things. I set the time to be positive, so after we've released the yo-yo and not before. I've set displacement to be positive. I want to know when it's moved away from the hand rather than returning to the hand and going through it. And the only time this is true is in between 0 and 3 for time. The question then goes on to ask us to find the maximum distance the yo-yo is from the child's hand, correct to 3 significant figures. So we've seen that we can use differentiation to find the maximum point, to find the maximum displacement in this case. So we'll go ahead and differentiate, and we'll use that to find the maximum distance from the student's hand that this yo-yo gets to. So ds dt is going to leave us with a quadratic. I've got 0.6 plus 0.8t minus 0.6 t squared. Now we could try to factorize this, but really I'd like you to use the equation solver on your calculator or the quadratic formula, and we get two results. Either t equals negative 0.54 or t equals 1.87. Okay, so like I've said before, the negative time would be before we've released the yo-yo, so that isn't going to be sensible or useful in this case. Time equals 1.87, that's the value we're looking for. That's the value that would lead to our maximum point. The negative would lead to the minimum point on the diagram. Okay, now that I know the time that this displacement happens, I'm going to substitute into the original displacement function, and that should tell me the actual distance, the actual displacement of that yo-yo at that particular time. So S is going to equal 1.21. So just being really careful here, I made sure that I started with a diagram so I knew the context in which I was working in. So I had some graphical context to what we were working with. Then I differentiated to find the maximum point. So that was the reason I was differentiating, because I wanted to find the maximum point according to the diagram. Found values for t. One of them was invalid. After I found that value for t, I just checked the question again. The question wanted us to find displacement. So I substituted that t value into the displacement function.